Good afternoon, ladies and gentlemen. Next Generation Networks, the Future of Global Connectivity, Riga Technical University, Associated Professor Tom Salgals. First of all, I want to a little bit introduce. We are the leading in fiber optical communications in terms of high-speed data transmission, in the achievements of the world records also in this field. And our interests are for WDM fiber optical access networks to provide more capacity, higher data rates, and of course also for the 5G and 6G development and beyond the 5G, the 6G, and of course also the radio or the fiber implementation, therefore for the terahertz communications. So passive optical network analysis in terms of the reach of the 50 kilometers, data center interconnects, the distances which is around 10 kilometers. And there is like the globally problem with these data centers at the moment. Then is a lot of the warm of the telecommunication devices used. They are the bulky. Therefore, we are looking also for integrated photonic solutions there to implement with the higher data rate, making them smaller in the size, therefore provide novel achievements. And of course also optical frequency comps based on the microrods, microspheres, on the chip-based systems. And for today, for the classical communications and also for the quantum communications, I want to discuss and show novel achievements from the OR side. It could be used for the both of the system implementation. I want to show without any deep inside the technical realization, but also the results what we have. So optical frequency comps to provide the cheap, energy efficient communication solution, integrated photonics, miniaturized size, chip scale elements, free space optical communications. Today I will not discuss about the Big Bang theory, but the novae, new star, like shift to the skies with the optical signals and the transmissions between them, and the nanophotonics and optoelectronics, which are the fundamental background for applied innovations and implementation. So, optical frequency comps, there could be used different implementation techniques for the optical frequency comps, but first of all, I hope everyone is familiar with fiber to the home technologies. Like nowadays, fiber optical infrastructure are deployed almost everywhere. Therefore, this data connectivity what we have are provided by the optical fiber links. Also from the mobile phone, we have the microwave till the base station, but still the base stations are connected together by the optical fibers. Until the question is how we can make cost-effective, energy-effective, and spectral-effective solutions. Therefore, here today I will show also this implementation for the classical and quantum future communication systems. So they could be used like the spherical resonators, or the toroidal resonators, or even in the chip integrated rings or the toroids. As you can see here, for each communication channel in the optical fiber domain, we have the light beam. To make the higher capacity, we are using multiple channels, but where each of these channels consists of at least one laser source. Therefore, by this optical frequency comp introduction, we can use only one laser, and by the optical effects have like wide spectrum of the spectral tones and replace multiple laser arrays in the classical communications. So normally, here you can see comparison with the silicon microspheres and the microrods. The solutions what was designed by our team. So for the first time in the world we show, of course, previously also it was shown by the physics, but for the first time we showed that it's possible to use such kind of the technology to achieve cheap solution for these novel light sources, because we was the first one who achieved necessary amount of the power which was possible to use for communications. And from the left side, microrod resonators, collaboration with the Germany partners in the Europe, and silicon microsphere. Here are some experimental views from the laboratory. Basically, we imagine that we have only one tone. Now we have wide spectrum. We can apply for different use cases, not only in the telecommunications, but from the side of telecommunication operators, those who manufacturing this equipment stuff, it's quite important to get necessary space between these channels, therefore acquiring to the recommendations. For example, by the sphere we can achieve 400s, by the microrod we achieve 100 gigahertz, this space between these newly generated harmonics. And by ourselves we validate this technology and show this proof of the concept at the moment for scenario in the passive optical network and data center interconnect with microsphere up to 60 gigabit per second. Today, actually, before I come here, I had the speed test on my computer about the internet speed. It was around 100 megabits per second. That was not quite a lot, but still here, that's mean 0.1 gigabit, and here's the 60 gigabits per one channel what we can provide. And by the microrods, we achieve 100 gigabits per second for this one channel transmission. So about the integrated photonics, at the moment we are, by collaboration together with the partners, are aiming these ring resonators on the chip for the optical frequency comb generation with the new technology of the tantalum pentoxide with the interest of the testing and provide like this data transmission. So about the integrated photonics, we already have proved ourselves with several world records in the field of the communications by using like integrated photonic chips. We are collaborating with the IMEC, also with the Keysight. Therefore, our results, what we are using for the testing different kind of the devices on the chip, for example, Mach-Zehnder modulators, ring resonator modulators, also with the open electro-absorption modulator, we achieved the record of 380 gigabits per second. We are publishing in first-class world conferences, like in the Europe ECOC, European Conference on Optical Communications, the first one, in the USA Optical Frequency Communications OFC, in the post-deadline sections, like PDB. Therefore, our results become like the world records in this field. So about also designing, we have some competence here. Here is the silicon photonic chip, which is designed by our team members and produced by the IMEC, with whom we had established good collaboration. IMEC is the leading company in the Europe in the integrated photonic circuits, and by our product, this chip, we already show the performance by making smaller in the size these modulators. Therefore, it could be put inside in the transmitter side of this system. 245 gigabits per second per one channel by the using of the ring resonator modulators. And it is like the future potential also for the data centers because it's small by the size, less electricity needed for it to drive them. And of course also the heating. If there is no such big of the size, therefore not such a big amount of energy is necessary to use for the cooling systems. So collaboration with the Keysight, we also have R&D. They're interested in our testing possibilities and also the facilities and for the test of the newest equipment what they produce. Our achievements in the field of the integrated photonics was honored by Prime Minister Evi Kaselinja in 2023, and also we received like the biggest scientific achievements award from the Latvian Academy of the Science. So the next one, instead of the fiber optical communications, we can transmit also the light through the skies, therefore point-to-point communications for long distances, not like something similar what we have like the Wi-Fi for the computer, or we have like this microwave for the phone. We can transmit these signals to receive them by the data, but we don't see the same signal. Here is the same. By the human eyes, it's not possible to see, but by implementation of quantum cascaded laser, quantum cascaded detector, we prove also this field. It's something similar like 5G, 6G, where we are transmitting, but here fully optically light beam for the long distances. It could be used for satellite communications or for the ground communications, and the results of it we publish in the Nature Communications, like achievements of 70 gigabits per second for this transmission. And in 2024, we get like honored from Latvia Academy of the Science for the significant achievements in this field. So going to the next level, we also established like the nanophotonics direction at university. The main aim of this direction is to develop new models of the elements for classical communication systems and also ensure the implementation of future quantum communication systems. We already prove ourselves with different kind of these technologies, where the results are published in high impact papers, and also in the laboratory establish new device for the manipulate of the light at the nanoscale, for example, for the lab on the chip applications. And I think it's also partly important to mention that not only for communications it could be used, but also for targeted drug delivery or bio applications. So, okay, thank you very much.